Picture this. You're starving, you're in a rush, and your thumb completely slips on your keyboard while you're trying to order dinner. You type an absolute jumble of letters into the search bar, but somehow the app still knows exactly what you wanted. Your favorite pizza place pops right up. It kind of feels like magic, right? Well, as we're going to see today, that magic is actually the result of some incredibly complex heavy lifting engineering happening completely behind the scenes in just milliseconds.
Welcome to this explainer. I have always wondered how large-scale AI actually operates in the real world when millions of people are using it at once. So today, we're going to dive straight under the hood of Uber Eats together. We'll see exactly how they evolved their search from a basic, old-school matching game into this massive, highly intelligent global system. Okay, let's dive right into this. Here is our roadmap for today. We'll start with a problem with keywords, then move on to mapping meaning with models, look at the immense challenge of balancing cost and speed, and finally, how they handle safe and reliable updates. All right, section 1, the problem with keywords. Basically, why literal matching just completely fails us. So traditional search relies on what we call lexical search. Think of it as a really rigid, totally literal dictionary lookup. If you type mozzarella with one L, but the restaurant menu spells it with two, the system just comes up blank. Or think about the word apple. Lexical search doesn't know if you want a fresh piece of fruit or if you're looking to buy a phone from the tech company. Semantic search, on the other hand, is all about contextual awareness. It's actually trying to understand your true intent. And this perfectly illustrates why Uber Eats just had to upgrade. Think about the common lexical search traps we fall into every day. You have synonyms, where maybe you search soda, but the restaurant literally lists it as soft drink. You've got typos, like our mozzarella example, shorthand, like typing GF Pizza when you want gluten-free, and honestly, my personal favorite, language mixing. In Spanish, pan means bread, but in English, you're looking for a frying pan. If your search engine only reads raw letters, it's a total disaster. And in the delivery world, a bad search result means a user gets frustrated, bounces, and goes hungry. No one wants that. Which brings us to section 2, mapping meaning with models. Introducing semantic search. So, how does semantic search actually work? Well, it works by encoding both the queries, the stuff you type, and the documents, the restaurants and menu items, into mathematical vectors. Imagine a massive, multi-dimensional room. The model places these vectors so that semantically similar items are physically grouped close together in that space. That means the vector for soda and the vector for soft drink are next-door neighbors, even though they share absolutely zero letters. It's a fundamental shift from matching raw words to matching actual meaning. So how do they pull this off at scale? Uber Eats built a classic two-tower deep neural network to split the workload. Tower 1 handles offline document embedding. Because the catalog of restaurants is billions of entries long, they batch process all of this offline, generating vectors for every item and storing them ahead of time. Tower 2 is the online query embedding. When you hit search, the system calculates the vector for your specific query in real time. This entire architecture is powered by a large language model called Qwen, which Uber then fine-tuned with their own in-house Uber Eats data to perfectly map to their specific food and retail universe. Let's move to section 3. Balancing cost and speed, the enterprise scale challenge. Now, the stakes here are incredibly high. How do you make large-scale indexing affordable and lightning fast? I mean, if you were searching through a multi-billion document index using dense mathematical vectors, the sheer computing power required is staggering. Without some serious optimization, serving this at a global scale would simply break the system. It would cost an absolute fortune, and honestly, it would take way too long to load on your phone. The solution they found here is super fascinating. They basically shrank the precision of the numbers used in the vectors. By going from heavy float32 data down to much smaller integer representations, specifically int7 scalar quantization, they achieved a massive breakthrough. Latency dropped by over 50%, while the recall quality remained solidly above 0.95. Basically, they cut the waiting time in half without sacrificing the quality of your search results. But wait, they didn't stop there. They compounded this with something called Matryoshka representation learning, or MRL. Think about those Russian nesting dolls. You open one, there's a smaller one inside, and a smaller one inside that. MRL works exactly like that. It trains a single model to output embeddings at various lengths. If you need lightning speed, you just use the shortest doll. It captures the basic coarse information really fast. If you need extreme precision, you use the largest doll, which has all the fine nitty-gritty details. This gave them an unbelievable advantage. By serving smaller 256-dimension embedding cuts using this MRL technique, Uber Eats reduced their storage costs by 50%. literally 50%, and the loss in retrieval quality for English and Spanish, less than 0.3%. It's almost zero quality loss for half the storage cost. That is an absolute engineering home run. As one final speed boost, they apply these strict pre-filters before the heavy AI vector search even begins. They filter by your immediate location block, city ID, document type, and whether you want delivery or pickup. These are simple true or false filters that dramatically shrink the multi-billion document pool down to a highly relevant local subset right off the bat. This guarantees that when the AI finally steps in to rank the remaining options, it happens blazingly fast. All right, our final stop, Section 4. Safe and reliable updates, protecting the production environment. Normally, companies use a blue/green deployment. That means they build two completely separate copies of the whole system. But at this scale, maintaining two separate multi-billion document indexes is way too expensive. So Uber uses this incredibly clever single-index two-column approach. They have one index, but it has an embedding_blue column and an embedding_green column. They serve live traffic from one, say blue, while quietly updating the green one in the background. Once green is perfectly ready, they just flip a switch to make it active. It gives them perfect rollback flexibility without doubling their storage costs. But they don't just blindly flip that switch. They enforce strict automated validation gates to prevent catastrophic bugs from corrupting live traffic. First up, completeness. They make absolutely sure the document counts match the source tables so nothing gets lost. Second, backward compatibility. They ensure the column that didn't change is still byte for byte totally intact. And third, correctness. They literally replay real user queries in a safe environment and compare the new results against live production. They have to prove the update actually performs better or at least the same before it ever sees the light of day. But hey, human error still happens, right? Someone could accidentally configure the wrong model. So they added this brilliant runtime check as a final safety net. When the service is actively running, it constantly verifies that the ID of the model generating your search matches the ID of the model stored in the index. If there's a mismatch, it immediately logs an error. If it sees a few of these, it automatically rolls back to the previous version. This check protects against version mix-ups invisibly, without adding a single millisecond of latency to your search. And that brings us full circle. It is exactly this kind of thoughtful engineering, combining strong AI modeling, bulletproof infrastructure, and relentless cost optimization that delivers a search experience that feels smarter, faster, and perfectly intuitive. All those deep back-end tricks we just talked about directly result in the seamless experience of you typing a typo and still getting exactly the food you were craving. So I'll leave you with this final thought to chew on. We saw how Uber squeezed massive models down using in-7 quantization and Matryoshka dolls to save speed and cost. But as AI models inevitably grow even larger and infinitely more complex, how will future engineers find new, even more creative ways to shrink them down to fit right in our pockets? It's a fascinating frontier. Thank you so much for joining me on this explainer. I hope you found this deep dive as mind-blowing as I did. Keep learning, keep exploring, and I will catch you on the next one.